All right, well, we're now recording. Thank you for being online this morning with me. Uh, over the last 2 days, I've received a lot of messages of students in my class that have been having to quarantine. I don't think any of them are from y'all's class. Y'all's class is actually one of the few that I have that doesn't have really anybody out. But the reality is, my other three classes have between 4 to 6 people that are out right now in each class, and so that makes it kind of difficult. It's tough to juggle having students virtual and having students face to face at the same time. And I feel like neither one of them gets the best out of it. So I really want to make sure that we can cover this material well here for the next two classes. Uh, I hate that I don't get to see y'all face to face here for these last two, but I think it's probably the best thing overall. I said at the beginning of the semester that I'd do whatever it took this semester to make it a good experience for everyone, including the people that were offline, and to try to keep everybody safe. And so that's what this is about. I kind of hated to do it, but as more people were ruled out of my classes for, well, honestly, because of when it happened, I won't get to see them again. But I just felt like I had to do this. So we're going to take a look at antiderivatives today. Just a couple of quick announcements. The exam 3 review, all that material is up for you, including the practice exam. You can start taking a look at that at any point. Antiderivatives, which we'll cover today, is what's on Skills Quiz 10. Skills Quiz 10, I will upload the answer key for that on Saturday. So you should work that between now and Saturday. You're kind of on the honor system there to look at the answer key, grade what you have, and upload that for me this Saturday. And I believe your final homework set is also due on Saturday. This is a topic, antiderivatives today, that will be a bridge to things that we will discuss in Calculus 2. So if you want to think of this as your first Calculus 2 topic, you can. It is the majority of Calculus 2 will be spent on this topic and the applications of it. So let's go ahead and dive in, starting with a definition. So a function, and we use capital F for the antiderivative, is called an antiderivative of a function f of x if the derivative of the antiderivative is the function for all x in the domain of f of x. And then we use this peculiar sort of notation that I'm going to speak more to here in just a second, called the integral, the indefinite integral. It's the collection of all possible antiderivatives. Now, given that this is a definition without much context, I'm not completely certain that y'all understand the impact of everything that's there. So I kind of want to walk us through a couple of the notational aspects of this, and then we'll look at several examples of this today. All right, so the topic is antiderivatives. And it's really just, how do I undo a derivative operation? So you can think of an antiderivative as the inverse of the derivative operation. And, y'all been taking math classes for quite a while at this point. We're used to the concept of inverse operations. The inverse of addition is subtraction. The inverse of multiplication is division. The inverse of powers or roots, right? The inverse of a logarithm is an exponential. You're used to operations and having an operation that undoes it. I believe this will be the first time, I can't think of another example, this will be the first time where you can't completely undo an operation in mathematics. So let me kind of get you into it a little bit and explain what I just said. We're used to this progression in this course. You've got f of x, you take a derivative, and that gets you f prime. You take another derivative, that gets you f double prime. And that sequence can keep going. Now we're going the other direction. We use capital F to represent the antiderivative. If you took the derivative of this function, you would get the function that you start with, f of x. But the operation in the reverse direction, which undoes differentiation, that operation is called the antiderivative and goes by this notation. Now let me explain this notation real quick. If I say that the integral of f of x dx is equal to capital F, then this symbol is known as the integral. More on that in just a second. The function that I'm taking the integral of is known as the integrand. And then dx we know is the differential. It's the same differential that we discussed in class this semester. It tells me what we are taking the antiderivative with respect to. Now, given that this is our notation, I want to talk about the problem with antiderivatives. And there are going to be a lot of problems with antiderivatives. Taking derivatives is far easier than taking antiderivatives, and a simple example will illustrate that. Suppose you have the function 2x. Excuse me, suppose you have the function, 2x, let's just do 2x. Then what is the antiderivative of 2x?
X squared plus c.
Okay, so what I'm asking here, and I think I heard the correct answer there, what I'm asking here is what function has derivative equal to 2x? That's what should go here. Whatever function has derivative that's 2x is what should go here. So we know from class that the function x squared has the derivative 2x. The problem is, so does the function x squared plus 1, x squared plus 2, x squared plus pi, x squared plus any constant. All of these functions have the derivative 2x. It's like we did the following. It's like we took and started with x squared. We took a derivative. We got 2x. And now we've decided we want to undo that. We want to go back to x squared. Our problem is the operation going back is not unique. I cannot, without more information, I cannot return us to the function that we just came from, because the antiderivative operation says find me a function whose derivative is 2x, but that could be an infinite number of things. It's x squared plus c. So when I write x squared plus c, this is called the general antiderivative. So every time we compute an antiderivative today, all the examples we're going to do, and we're going to do several, every time we compute an antiderivative, you're going to see me write plus c at the end of it, because I can only determine uniqueness up to a constant. I can't tell you what the constant term of the function is if I use an antiderivative to undo differentiation. Now, with that being said, just like we had many different properties for derivatives, we're going to have many different properties for antiderivatives. And I'm going to start with those properties first, and then we'll do several examples together. One last thing before we get there, though. This notation, the integral whatever dx notation, this symbol was originally an S. So it was originally an S, and over time, mathematicians sort of elongated the symbol into what we call the integral symbol now. It stood for sum. So it turns out that the way that you undo a derivative is by taking a special sum. Now, we're not going to talk about that sum in this course. That's where we'll start in Cal 2. But it is a very strange symbol, and I just want you to understand that originally it meant take the sum of a bunch of little things times dx elements. That's how you undo differentiation. So if you think of this as being a sort of sum of this function over some small interval, then that makes it a little bit easier to wrap your head around the notation. Okay, let's talk about some of these properties. The first property is what we just got through discussing, that when you take the antiderivative or the integral of a function, you get its antiderivative plus a constant. That's the best you can do. If you take the derivative, so property 2, if you take the derivative of the antiderivative, those two things cancel out and just give you the function. If you take the antiderivative of the derivative, you get the function back, but since you take the antiderivative second, you only recover the function up to a constant. So property 2 and property 3 are basically the inverse properties for differentiation and integration, or taking the antiderivative. They offset each other. Just like with derivatives, if you had the derivative of two functions added together, you could take the derivative of each one separately. Well, you can do the same thing with antiderivatives. If you have the antiderivative of a function that added to another function, you can take the antiderivative of each function separately. If you have any scalar multiples, meaning constants that are multiplied by a function, remember that you could factor those out when you took the derivative. You can do the same thing for the antiderivative. You can factor out any constants before you take the antiderivative, then just take the antiderivative and multiply it by the constant. Finally, this last one is related to chain rule. So if you had a function whose inner derivative had a derivative of a, then if you were to take the derivative, you would multiply by a because of chain rule. So the inner derivative here is a, so you would end up multiplying by it. Well, since the antiderivative undoes that, you no longer will multiply by a, you actually divide by a to undo it. I'm going to say more about this property as we go through it here in a little bit. But these are the sort of 6 major properties for getting started working with antiderivatives. All right, let's look at an opening example, and we'll do several examples together. For Calculus 1, the most important formula for you to know and be able to work with is the power rule formula. So the way that you should think about power rule is simply undoing what the derivative does. So let me show you a quick example to motivate this, and then we'll discuss the actual rule and do some examples together. So we know that if you take the derivative of x to the n, that is n times x to the n minus 1. So another way of thinking about that is if I start with x to the n, take the derivative, then I get nx to the n minus 1. Now I want to undo that. So the question is, how do I undo that? Well, if you think about the steps needed to undo it, what you did was you multiplied by n, right? So how do I undo that? Well, I divide by n, right? So if I multiply by n, I divide by n, and I subtracted 1 from the power, so I should take that and add the power back in. So you can see that if I did those two operations, if I had multiplied by n in the derivative and divided by it here, and if I subtracted 1 in the power and added it back in, then you can see that that'll give me 1 over n times the n that's already there, right? So 1 over n times the n that's already there. Those operations cancel out. And then if I add or subtract from the exponent to get it back, that'll bring it back to x to the n. The point is there are two things involved. You have to divide by any powers that got brought down as a result of doing the derivative, and you have to add back any powers that were subtracted from doing the derivative. So the way this formula works is typically we want to come back to the function f of x. So we've taken some derivative. We're now at the function x to the n, and we want to come back. So how does that look if we're trying to come back? Well, it looks like the example above right here, but we're not dividing by n, we're dividing by whatever the power is here plus 1. Right? So you've got n minus 1 there, you're dividing by the power plus 1. So if the power here is n, then you're going to divide by the power plus 1 times x to the n. And here we added 1 to the power, so I'm going to add 1 to the power. That's how you get back. So the formula that we use is that the antiderivative of x to the n is x to the n plus 1 over n plus 1 plus a constant. Remember, the plus a constant is because I cannot uniquely go back to what I started with. The easiest way to remember it is whatever the power is, you add 1 to the power and divide by the new power. That's the best way to remember how to do this. So let me do several examples with you. And then there is an example that's being asked in learning catalytics question here. If at any point you feel comfortable answering that, go ahead and do it as I'm working on these examples. All right, so first example, what if I asked you to look at the antiderivative of the function 8x cubed minus 9x squared plus 4? So antiderivative or integral of this function dx. Well, our properties say that I can take the antiderivative of each piece and understand here, when you write the function, it's this dx is technically multiplied by all of these, right? So that's the notation that we use. So when I distribute this integral to each piece, the dx comes with each piece. That'll be made more clear in Calculus 2 why that is the case, but that's the standard that we use for our notation. So when you distribute this, you'll get 8x cubed minus 9x squared plus integral. I'm going to say 4 dx. 4 is a constant there, so that's 4 integral dx. So I'm using two properties here. I'm using the first property is that the integral can distribute to each piece, and that if I have any constants, I can pull the constants out of the integral. So let's start with the first piece. You've got the antiderivative of x cubed. Well, that is x to the 3 plus 1 divided by 3 plus 1. That is power rule. That's the formula that we just established right here. And then you've got minus 9 times the antiderivative of x squared is x cubed. So x to the 2 plus 1 over 2 plus 1 plus, and now this one's interesting. You've got the antiderivative of dx. Well, dx is the differential of x, or the change in x, and the antiderivative undoes change. So the antiderivative of the change, those two things cancel, leaving you with just x. So if you ever have the antiderivative of dx, the answer for that is just x. And remember, I can't do this uniquely. So I can recover the correct answer up to a constant. So I have to add a constant of integration there at the end. Technically, every time you do one of these, like here you produce a constant C1, here you produce a constant C2, here you produce a constant C3, but they are all arbitrary constants. And so I lump them all together as one big constant for the entire problem. So rather than have three little constants each time you do the antiderivative operation, you can lump all of the constants together as one big constant. All right, if I then make this a little bit nicer, the final answer here is this function. So this is called the general antiderivative. Now, since this is our first example, I'm going to check that this answer is correct. I won't keep doing this on the future examples, but you can check your answer. The way that you can check your answer is by taking the derivative of your answer and see if it matches what you started with. So the derivative of 2x to the fourth is 8x cubed. The derivative of minus 3x cubed is minus 9x squared. The derivative of 4x is 4, and the derivative of a constant is 0. So if you take this and match it to the integrand that you began with, you should get the same function. That's a way for you to check your answer is correct. All right, so I'm going to continue to do more examples. I'll pick up the pace on these next couple of examples, but I wanted to do this first one kind of slowly and explain all the steps. All right, so next up, what about the integral of the cube root function? So how do we take the antiderivative of that function? Well, I need to write it as a power, so I can use power rule. So it's x to the 1/3. And I know that power rule says you take the power and add 1 and then divide by that new power plus c. So this would be x to the 1/3 plus 1 is 4/3. And so I would be dividing by 4/3, but that's the same thing as multiplying by 3/4. So there's the best answer for this problem. So that is the antiderivative of the cube root function. All right, another example, what about the antiderivative of, let's say 1/4x squared? So I encourage you, until you become better at taking antiderivatives, to make use of all of the properties that we started with. So there's a constant here, 1/4, pull it out. So this is 1/4 integral. What's left is 1/x squared, but that's x to the -2. So I encourage you to use properties to make it very apparent that you're just doing the power rule on x to the -2 for a problem like this. So that's 1/4 times, now if I go to take the antiderivative, it's x to the -2 plus 1 divided by -2 plus 1. So that's 1/4 x to the -1 over -1, which is -1 over 4x. If you have any questions as we go through this, either say something in chat or ask me a question about it. Happy to answer them. All right, another example. What if I asked us to look at the integral of x times x cubed plus 1? Now, here is a problem that we will solve in Cal 2, but there's a way to get around it now. And that is, how do we undo a product of two functions? So we know from class that when you take the derivative of a product, you have to do product rule. So what we're going to be faced with in Cal 2 is, how do I undo product rule? If a product rule has been done, how do I then undo that? Well, luckily, we're not going to have to mess with that here. Instead, what I can do is simply distribute this x and turn this into a polynomial, which we can use power rule on. But that's going to be a big question for us in Cal 2, is what do we do if we have functions divided or multiplied inside an integral like this? But here we can get around it by doing a little bit of algebra. Distribute the x, and we get x to the fourth plus x, the antiderivative of which is x to the 5 over 5 plus x squared over 2. All right, and one last example here before we move on to some more rules. X squared plus 2x minus 3 divided by x to the fourth. It's the same comment that I made on example 4. That is, we're undoing a product that's going to be problematic for us in Cal 2, just like undoing a quotient is. So imagine that you've done quotient rule. How do we undo that? Luckily, because of some algebra here, I don't have to mess with that here. This is the same thing as x squared over x to the fourth plus 2x over x to the fourth minus 3 over x to the fourth. So I can distribute to each piece. That's x squared over x to the fourth is x to the negative 2. This one, factor out the 2. X over x to the fourth is x to the negative 3. And then factor out the 3. And this one is x to the negative 4. So remember, you're adding 1 to the power rather than subtract, like when you do power rule for derivatives. When you do power rule for antiderivatives, you have to add to the power and then divide by that power. So adding 1 to the power is going to make it negative 1, divide by that power. Here, adding 1 to the power is going to make it negative 2, divide by that power. Add 1 to the power is going to make it negative 3, divide by that power, plus a constant. So this will be negative 1 over x. Here the 2's cancel out. So that's also going to be negative 1 over x squared. Here the 3's cancel out, but you've got 2 negatives, so it's going to be positive, so it's going to be plus 1 over x cubed. So there's the antiderivative for that function. So that's pretty much all you can expect out of power rule. There's not much more example-wise for me to show you here. It's just the reverse of what we did for derivatives. So if you haven't answered the question yet, go ahead and respond. Go ahead and tell me what the derivative is of the function that's there for you.
So what were we talking about? Are we going to go over the other form? You said there was a general form, and then you talked about another form for like just general antiderivatives, and then there's a second one.
Yeah, these are all general antiderivatives. The second form is we're going to figure out, but we need more information to do it. We're going to figure out what the constant C is, right? So we're going to go back to a specific antiderivative with some examples. We may not get to that today. That might end up being Friday, but we need more information to go back to a specific integral. So the problem that you're being asked to work on is the integral of x cubed. The integral of x cubed minus 1/2 x squared plus 2x minus 4. So I'll give you about a minute to finish up an answer for that and enter it. And if you need the login, there it is. You know, these are going to be on test 3. They are going to be on the final, but we will go over them again at the beginning of Cal 2. So this is one of those things that as we work on it, you're really working on and working towards things for Cal 2. All right, so here are the responses, several correct ones. The correct answer is down here, x to the 1/4 x to the 4th. So you're taking x cubed, adding 1 to the power, dividing by the power, minus 1/2 x squared. Its antiderivative is minus 1/6 x cubed. The antiderivative of 2x is x squared, and the antiderivative of 4 is 4x. All right, let's take a look at several more formulas here. So this is a table. Your book has a similar table. This is a table of antiderivative pairs. And I'm going to keep this table up as we do more examples together for you to look at and kind of consult. You will not be given a table like this. So I don't know if I want to call this memorization just yet, but you need to be able to understand these derivative antiderivative pairs. If it's a more difficult formula, then yeah, I'll just give you the antiderivative formula. But the things that are on this page are not difficult. They're just the opposite of things we've already done this year. So for instance, we just did power rule here. Earlier in the course, we know that if you have the function e to the x and take its derivative, you get e to the x. But if you take its antiderivative, well, you're just going backwards, and that's just e to the x. So here, if I take the derivative of natural log, I know that it's 1 over x. So if I take the antiderivative of 1 over x, well, that's just natural log. Basically, these form a pair. So if you go forward, then you go backwards to get back to it. The same thing is true of cosine and sine. And this one I'll say a little bit more about. You know, we talked about, so this is antiderivatives of sine and cosine. You know, earlier in the course when I showed you how to remember the derivatives for sine and cosine, I showed you this little unit circle trick. And the trick there was, if you think of where, which functions have the value 1 on this circle, well, that's cosine has the value 1 there, sine has value 1 there, negative cosine has value 1 there, and negative sine has a value of 1 there. And all semester, we've been rotating this direction to take derivatives. So if you rotate clockwise around the circle, you're taking a derivative. However, if you rotate counterclockwise, then you're taking an antiderivative. So to get an antiderivative of a sine or cosine function, you simply rotate counterclockwise on the unit circle. All right. So the antiderivative of the derivative of cosine is minus sine. The antiderivative of cosine, though, is positive sine. You rotate in a different direction. We know that the derivative of tangent is secant squared. That was one of the ones that we memorized. So the antiderivative of secant squared is tangent. We know that the derivative of arctan is 1 over 1 plus x squared. So the antiderivative of 1 over 1 plus x squared is arctan. And the same thing for arcsine. So these are just what I expect you to know, right? These are some of the basic derivative formulas that we've looked at and the pairs that they form and how to undo them. Some of the ones that are a little bit harder are when you have values other than just x inside the function. How do you handle that? And I'll talk about those kind of on a per case basis here. But these are sort of special antiderivative formulas that we'll look at together. All right, so let's do several examples, and I'll keep this up so that you can refer back to it or copy it down in your notes while we're working on these examples. So here, I'm not going to be doing power rule anymore. So all of these antiderivatives are based off of derivatives that we've seen in the course, and we're just mentally undoing them. That's probably the best way to think about it. So first example, what is the antiderivative of 1 over minus 3x? Well, if I look at that function and I take the constant out, the constant there is negative 1/3. So I'm left with 1 over x. Now, I know you might be tempted. Oh, y'all can't see it, can you? There we go. So if I looked at the antiderivative of 1 over minus 3x, I take the minus 1/3 out, and I'm left with the antiderivative of 1 over x. At this point, you might be tempted to try power rule. You might say, oh, well, that's just 1 over x is just x to the negative 1. So if I do power rule, it'll be add 1 to the power, divide by the new power. What's the problem with that?
That would be a 0 in the denominator.
Yeah, you'd be dividing by 0, which is why the function 1 over x is not a power rule antiderivative. And the reason it's not a power rule antiderivative is you can't get the function 1 over x by taking the derivative of a power function. It turns out that the function 1 over x, this comes from taking the derivative of natural log, right? That's how you get the function 1 over x as a derivative. So if I'm going to undo the function 1 over x, I've got to send it back to natural log. So at this point, I've got minus 1/3 integral 1 over x dx. Well, that's minus 1/3 times the natural log of x plus a constant. Okay, example 2.
Sir,
Yes.
one question. I also notices in one of the formulas you gave us that x cannot equal negative 1. Is this what you were talking about, or is the actual like base?
Yes. So in the
Okay.
power rule, if you go back to the original definition of the power rule that was on that first page, it is only valid for powers that aren't negative 1. Right. So
Okay.
so power rule, the definition of power rule is that the antiderivative of x to the n is x to the n plus 1 divided by n plus 1, provided that n is not negative 1.
Okay.
Right. So I can't use power rule on the function x to the negative 1 because x to the negative 1 goes back to natural log. It doesn't go back to a power. All right, let's try this next one. What about e to the 4x plus 3? So if I'm thinking about this function, then I'm thinking about the fact that, well, if I was to take the derivative of e to the 4x plus 3, that would just be itself, but I would have to multiply by 4 because of chain rule. So that's what this problem would look like if we were taking a derivative. So we understand that if I'm trying to go backwards, right? If I'm trying to go backwards, how do I undo this, right? So I undo it by, instead of multiplying by 4, I actually end up dividing by 4. So that's the antiderivative here. I just acknowledge the fact that the antiderivative of an exponential is an exponential because the derivative of an exponential is an exponential. But whereas the derivative would have me multiply by 4, the antiderivative has to undo that. So I have to divide by 4 instead. And that should say 4x plus 3, not 4x plus c.
You wouldn't add 3, like do something with the 3 there, going backwards?
No, because this isn't a power function, right? So the derivative of e to the x is just e to the x. So if I try to go backwards, right, the antiderivative of e to the x is just e to the x. You don't do anything to the power when you take the antiderivative. But because of chain rule, I would have been multiplying by 4 when I take the derivative, so I have to divide by 4 to undo that. All right, let's try another one. So what if I asked you to look at this antiderivative? Can you find something in the table that fits this?
Wasn't it one like arcsine or arctan? I think arctan has a square root in the denominator.
Yeah, arctan is the closest one, right? Because we know that the derivative of arctan is 1 over 1 plus x squared. And you might be thinking, well, but that's a 1 and that's a 9. How do I do something with that? Well, the way that you can make it fit, right? Because really I'm just trying to make this look like a function whose derivative I know, right? That's all I'm trying to do. And the way that you can do that is by dividing by 9. So if you divide both the top and the bottom by 9, you'll get 1/9, 1 plus x squared divided by 9. And so now that's looking a little bit better. Okay, that's looking a little bit better. But you have, I'll pull out the 1/9. And now you have 1 over 1 plus, rather than write it as x squared over 9, I'm going to write it as x over 3 squared, like that. So now this looks like arctan, because it's 1 over 1 plus something squared, right? So, you know, if you want to, you can think of this as a formula that is whatever goes here gets squared there. So what we have to think about now is, okay, so what's clearly in the formula is x over 3. So what would the derivative of the arctan of x over 3 look like? Well, it would look like 1 over 1 plus x over 3 squared. That's what the derivative formula would be, which matches this perfectly. However, I know when I take the derivative of this, I'm going to multiply by 1/3 because of chain rule. So I'm going to have a 1/3 here. But I have a 1/9 here. But that's easily solved. I can just take 1/3 there and 1/3 here. And now it matches up. Now this is identically this, right? So you've got a match. You know that the derivative of arctan looks like this, and I've managed to manipulate this so that it looks like the derivative of it. So I know that the antiderivative of this is the arctangent of x over 3. Now that's a little bit on the difficult side, and for some students, they don't want to mess with that. They want to just memorize their way through it. And that is an option. I think long-term, that's an option that will hurt you. I think trying to think your way through these problems is much better. But if you struggled with this manipulation here, then, you know, an option is right here, learn that 1 over a squared plus x squared is 1 over a arctangent x over a. And that's what we just used in that problem, is we used that formula to do that problem. but I'm trying to think of it. I'm trying to get you to think of it from a different perspective rather than just memorizing formulas, trying to get you to think of, okay, well, I know the derivative of arctan looks like this. How can I make the antiderivative look like this as well so that I can easily represent it with a function I know? And that's what this all comes down to, is rather than trying to memorize both sides of the issue, meaning you already have memorized all these derivatives and derivative formulas, don't waste that. Use that to tell you what the antiderivative is going to be, rather than memorize both sides, right? Don't now go and memorize a bunch of antiderivatives. Just use the fact that you understand how derivatives work to undo them. That's the ultimate goal for getting good at this. All right, let's do another one. What about the antiderivative of, let's say, theta squared? Change variables on you here. Secant squared theta d theta. All right, so if I'm looking at this, then I can take the antiderivative of each piece. And it's just a question of, do I recognize their antiderivatives? Well, this one's a power function. So I can use power rule on the first one here. It's just theta to the 2 plus 1 divided by 2 plus 1. So that's just theta cubed over 3. I know how to handle that. That's just a power function. And now I have the antiderivative of secant squared. So do I know a function whose derivative is secant squared?
Tangent.
Tangent. So since the derivative of tangent is secant squared, the antiderivative of secant squared is tangent. And so your answer here would be theta cubed over 3 plus tangent theta plus c. All right. Last
for your
example.
answer, would you also accept 1/3 theta cubed?
Yeah, 1/3 theta cubed is fine.
Okay, just making
Same
sure.
thing. So last example, and then we'll call it a weekend, or we'll call it, no, we won't, because it's not Friday. I'm used to doing this with y'all on Friday. I'll see you back here on Friday after this next example. All right, so we've got the antiderivative of secant theta times quantity tangent theta minus secant theta. Now, you know, this is where you can game things a little bit, right? You know, if I'm asking you this question, then I'm not expecting you to know some weird formula from Cal 2 that we'll talk about once you get to Cal 2. So there must be a way to algebraically manipulate this into something that you recognize. Well, there is. If I distribute the secant, notice that I get secant tangent minus secant squared. And you just told me that the antiderivative of secant squared is tangent. So we know at least 1/2 of this. We know that this part is tangent. What about this part? This is a derivative that we didn't talk about much this semester, but do y'all remember it? What function has derivative secant tangent?
Secant.
Yeah, that's the secant function. So the derivative of secant tangent is secant. So this is secant theta. So there's my antiderivative. All right, we're going to do more with antiderivatives next time, including going back and giving you more information so that you can find a specific antiderivative, and then looking at some word problem applications for antiderivatives. But I feel like this is a good start. This will get you to where you can do a lot of the problems that are on that skills quiz, a lot of problems that are in the homework. Start thinking about these antiderivative rules and antiderivative formulas. All right, y'all have a good day.
Is it okay if I ask you a few questions about the exam study guide?
Yeah, that's fine.
Mainly just some of the definitions for the theorems.